Once the core has shrunk and heated up to around 100 million Kelvin, then it is now hot enough for helium fusion to begin. Now, the reason why we have to have a higher temperature for helium fusion is because we now have two protons in the nucleus, meaning we have double the charge, and if you remember, positive and positive repel. So because of that, they have to be going faster to get close enough to actually fuse, so we have to have a much higher temperature. Now, because of the way that electron degenerate matter behaves, everywhere throughout the core is going to reach the same temperature at the exact same time, meaning that the entire core will suddenly begin helium fusion in the same instant. This moment where it suddenly begins helium fusion everywhere throughout the star, this is what we refer to as the helium flash. On the HR diagram, it's right up here at the very top of the red giant branch. So we have our red giant stars, and then right up here we have the helium flash. Now, helium fusion follows what we refer to as the triple alpha process. A helium nucleus is also referred to as an alpha particle, which means we're going to be fusing 3 helium together, and this will then produce 1 carbon. So we have 3 helium turning into 1 carbon in this process. Now, it's also possible in this process for it to pick up an extra helium, which will turn it into oxygen. These stars that have active helium fusion in their core are sometimes referred to as helium fusion stars or horizontal branch stars. Notice that this line through here is basically horizontal. In fact, pretty much all astronomers that I'm familiar with refer to these as horizontal branch, not helium fusion stars. Well, as this happens, the core is going to expand because we have that fusion. As the fusion increases, the core expands. As that core expands, that means that the shell fusion layer is actually going to have less gravity squeezing in on it, so it's going to cool off as well, which leads to a decrease in the overall fusion rate, which leads to less pressure through the rest of the star. If we have less pressure in the rest of the star, then gravity wins, and the outer layers are then going to shrink. So notice that just like before, we have the opposite trend. Before, as the core shrank, the rest of the star expanded. In this case, as the core expanded, the rest of the star shrank. Now, as the rest of the star shrinks, the outer layers are going to heat up, and it's going to become less luminous because it's now smaller. So we see these stars swing over to the left onto what we refer to as the horizontal branch. We can actually see stars in all of these different stages as we look at globular clusters. So this is actually an HR diagram of a globular cluster. The stars along here, these are on the main sequence. Right here, we have the main sequence turnoff point, so these are the stars that are just now leaving the main sequence, having finished using their hydrogen in their core. Along here, we've got the red giant branch, where we have a non-fusing, inert helium core and a shell of hydrogen fusion. Up here at the top, these are the stars that are getting ready for the helium flash. The helium flash is that instant where they suddenly begin helium fusion. Once helium fusion begins, the stars shrink and heat up, moving over to the left onto the horizontal branch. In a horizontal branch star, we have ongoing helium fusion in the core and a shell of hydrogen fusion surrounding that core. A star like the Sun will remain on the horizontal branch for about 100 million years. Now, eventually, these stars are going to convert all of their helium into mostly carbon and a little bit of oxygen. When that happens, then there's no longer going to be fusion in the core, so again, the pressure drops and the core begins to shrink. It will again continue to shrink until it reaches electron degeneracy pressure. However, as it shrinks, it is then going to trigger a shell of helium fusion. So we'll have a non-fusing carbon core with a shell of helium fusion and a shell of hydrogen fusion. As the core contracts, this leads to greater amount of fusion in the two shells, and with greater fusion, we're going to get a greater pressure. So the rest of the star is again going to expand. So these stars are referred to as asymptotic giant branch stars. If you remember back to math, I remember talking about this in algebra. An asymptote is a line that gets close to another line without ever actually crossing it. So these stars are getting close to the giant branch, but not actually crossing it. That's why these are asymptotic giant branch stars. But more often than not, it's just easier to call them AGB. So these are also AGB stars. Now, during the star's red giant and asymptotic giant branch phases, it is possible to have what are known as dredge-ups, where we have convective cycles that go all the way down to the core and back out to the surface. This is going to bring those heavier elements up to the surface. So it is possible to actually see some stars that have a higher content of carbon in their atmospheres than normal. These stars that appear to have a higher content of carbon, we cleverly name carbon stars, with this carbon having been pulled up. Now, as these stars die, those outer layers are going to be lost into space, which is going to increase the amount of carbon and oxygen in the interstellar medium. During this AGB stage, the star will have swollen up so much that the outer layers are held on by gravity very, very weakly. What this means is that any bump in pressure will actually cause these outer layers to begin to drift off into space. Then the other layers surrounding the core will then get ejected from the star through a series of what are known as thermal pulses. A thermal pulse is a sudden spike in the fusion rate of the helium shell that's surrounding the non-fusing helium core. Well, these layers, as they move out away from the star, are still going to be very, very hot, which means they're going to be giving off their own light. So we end up with this bubble of glowing gas surrounding the star. This bubble surrounding the star is what we refer to as a planetary nebula. Now, this could be the worst named thing in all of astronomy. It has nothing to do with a planet, but we refer to it as a planetary nebula anyway. So this shell is going to continue to expand. Now, after around 50,000 years, the nebula will have expanded and cooled off enough that it's no longer going to be visible. It's then going to mix with the interstellar medium, which is going to increase the amount of carbon, oxygen, and nitrogen within the interstellar medium. A typical star will actually produce several of these planetary nebulae during this stage. Now, low-mass stars never get to the pressure or temperature necessary to begin carbon fusion. So once the core has reached carbon, fusion ends. Now, eventually, all of the outer layers are going to be lost to space, so we're left with just the non-fusing carbon core. This thing that is left over is what we refer to as a white dwarf. Now, the white dwarf is only held up against gravity due to electron degeneracy pressure, and it is also going to be really, really hot. So it's very, very small and very, very hot, which is why we refer to it as a white dwarf. So the white dwarf is the stellar remnant, is the corpse of a low-mass star. And in other words, if we return to the solar system in around 7 billion years, we're going to find a white dwarf. We can summarize the entire life cycle of a low-mass star using the HR diagram. So we start out with a protostar, which is going to be over here in the top right. As it shrinks and heats, it's going to somehow find its way down onto the main sequence. All stars on the main sequence are in the process of hydrogen fusion, converting hydrogen to helium. Once all of the hydrogen is used up, we now have a core that is just helium, which causes the core to shrink until it reaches electron degeneracy pressure. But as it shrinks, it ignites the layer of hydrogen shell fusion. That shell is then going to supply pressure for the rest of the star to expand. The star is then going to swing up and to the right onto the red giant branch. As the star is on the red giant branch, eventually the core, the non-fusing helium core, is going to get hot enough that in an instant it's suddenly going to begin helium fusion. That's the moment of the helium flash. After the helium flash has happened, the core is going to expand, and the rest of the star is then going to shrink because of a decrease in that hydrogen fusion layer. So the star is going to swing down onto the horizontal branch. So a horizontal branch star has active helium fusion in the core with a shell of hydrogen fusion. Eventually, the star is going to use up all of the helium, turning it into carbon with a little bit of oxygen, and so fusion is going to end in the core. So the core is then going to shrink, the shell fusion of the hydrogen shell, and then it will also trigger a helium shell, is going to then increase, leading to an increase of pressure, so the rest of the star then expands onto the asymptotic giant branch. As the star is on the asymptotic giant branch, we'll get flare in the helium shell, the thermal pulses, which create planetary nebula until the star finally ends as a white dwarf, where the white dwarf is the exposed core of the now dead star. Alright, let's see if you've got all of the different phases in order. Here is our 5th lecture quiz question. Which of these has the correct order for the life cycle of a low-mass star? A. Protostar, helium flash, red giant, main sequence, horizontal branch, asymptotic giant branch, planetary nebula, white dwarf. B. Protostar, main sequence, red giant, helium flash, horizontal branch, asymptotic giant branch, planetary nebula, and white dwarf. C. Planetary nebula and white dwarf, protostar, main sequence star, red giant, helium flash, horizontal branch, asymptotic giant branch. Or D. Planetary nebula and white dwarf, protostar, main sequence star, asymptotic giant branch, helium flash, red giant, horizontal branch. Go ahead and think about it, and we'll discuss in just a bit. Alright, so which of these is the correct order? It is B. The correct answer is B.